All right, so this is stoichiometry. Stoichiometry deals with production of chemicals, and it will discuss everything we've sort of done, the periodic table and balanced equations and whatnot. So let's get into that here. We always kind of start with something that's a little more that you would understand than chemicals. So if we were in class, I would have you building these cars out of Legos. And what you would notice is every car needs one body, right? You need that one black piece, this piece here, to make this car. You need one of these yellows. You need two fenders, one over each of the back tires, and then you need four tires. And that's how you're going to make that car. So if I gave you this many pieces, and the question was, how many cars are you going to make? You know, since there's one of these for every car, that's going to make 10 cars, and that's not surprising to anybody. And you know, because there's one of these yellow bricks in every car, that's going to make 120 cars. So you already know that even though we have enough yellow bricks for 120 cars, because we only have enough of these axles and bodies to make 10 cars, we're not going to make 120. We're actually going to run out of those bodies first. Now the fenders, there's two. So there's two fenders for every car in one car. So that actually is going to limit us as well. We're only going to be able to make 7.5 cars out of the fenders because 15 divided by 2 is 7.5. So what about these tires? How many cars are we going to be able to make with those tires? Well, we know there's four tires in every car, right? There's four tires for every car. And therefore, that's going to be able to make 10.5 cars. So even though we have enough tires for 10.5 cars, and even though we have enough yellow bricks for 120 cars, and even though we have enough of these bodies for 15 cars, we're limited by our fenders. Our fenders are only going to make 7 cars, and so therefore we're going to have to stop at 7 cars, and we're going to have some leftover tires, and some leftover yellow bricks, and some leftover of those bodies. So this is no different than what we do chemically. Chemically speaking, we are trying to make some product, and if we have the amounts, the number of each thing that makes that product, we can figure out how many products we make and what we'll run out of. All right, so now let's say someone's a little lazy and they didn't want to count all the tires. They just found a canister of them and they're like, hey, you know what? We have 39.1 grams of tires. So this information can be helpful if we know how many actual tires, what the number of tires are in that 39.1 grams. And it turns out every tire weighs 1.71 grams, 0.71 grams per tire. So therefore, if we can change this 39.1 grams of tires into the number of tires, we're going to know how many cars we can make. So we know there's 0.71 grams in one tire, right? So that's going to give us, turns out to be about 55 tires. And from this information, we can now figure out how many cars by using the relationship that there's 4 tires for every car. So we were able to first convert that grams into the number of tires we had because that was the only information we were going to be able to use to figure out how many cars we could get. So let's figure that part out. We are able to, with 55 tires, and we know that every car has 4 tires. So we are going to be able to make, because of all this, the 55 divided by 4, so that's 1, remainder 1, and that's almost 4, but it's 3, with a leftover of 3 tires. So we can make 13.75, or basically 13 cars out of that 55 tires, which we figured out from the grams of tires. And that is what we're going to be doing in this unit. We need to figure out how many numbers of things we have if we have grams. So, and what we're doing now is the mole. And the mole is what the balanced equation is using. So we have water coming from oxygen and hydrogen. It takes 2 moles of water for every, or 2 moles of hydrogen for every 1 mole of oxygen to give you 2 moles of water. So let's do some of this stuff out now. So you read the question, and all the time in the question, there's going to be a given number, and that number is what you're starting with. So in this case, it's 3 moles of oxygen. And then you're also going to look for this how many. I'm going to switch colors here. So how many moles of hydrogen? So you're looking now at hydrogen. So you need to go to moles of hydrogen from moles of water, of oxygen. So we're going to start with that given. And we're going to want to cancel out moles of oxygen. So it's very important that you actually keep your labels, the moles and what it is you're talking about, oxygen, so that you keep everything straight. Now we need to get out of moles of oxygen and get into moles of hydrogen. And in order to do that, we're going to need the assistance of the balanced equation. So this balanced equation here, 2 moles of hydrogen for every 1 mole, understood that since nothing's written here, that's 1 mole of oxygen. That will allow you to cancel moles of oxygen. And now all you're going to do is multiply the tops and divide by the bottoms. So 3 times 2 is 6, and that's moles of hydrogen, and it's going to be divided by 1. So it's moles of hydrogen. So that's how you do that. So this balanced equation gives you a mole-to-mole relationship, and it allows you to change from one substance to another. Here we change from oxygen to hydrogen. And you're going to need that for everything we do in this unit. So notice what I did differently here. Only word that changed is now we're doing grams. So we're starting with 3 grams of oxygen instead of 3 moles. And we still are looking for how many, this time we're looking for grams of hydrogen instead of moles. So we need grams of this, and we're starting with grams of oxygen. So we're given 3 grams of oxygen, and we need, in this case, grams of hydrogen. So it's similar to what we just did, although it's going to be a little more in depth. And it's more in depth because now instead of just going from mole to mole using the balanced equation, we're going to have to get out of grams. And if you recall, we get out of grams using the periodic table. So 3 grams of O2. If you go to the periodic table, you're going to see oxygen, which is number 8, has a mass of 15.99, or basically 16.00. So we're going to use that number there. And since there's 2 oxygens, we're going to need to multiply that by 2. So there's 32 grams of oxygen for every 1 mole. For every 1 mole of oxygen. Remember, anything on the periodic table is good for 1 mole. So that gets rid of grams of oxygen. Now we have moles of oxygen. So now we're going to need that mole-to-mole relationship. So we look to the balanced equation for a mole-to-mole relationship. And we're going to get out of moles of oxygen and get into moles of hydrogen right here. All right. And so you see here, so this is coming from the balanced equation. So that's 2, right? Because that's what the blue thing is. And the red thing that we're getting rid of is an understood 1 mole of oxygen. And moles of oxygens are gone, and we got moles of hydrogen, but we need to go to grams of hydrogen. So again, we're going to need to consult our periodic table. And on the periodic table, hydrogen, which is number 1, will have basically 1.01 grams at the bottom. So to get rid of moles of hydrogen and get to grams of hydrogen, we're going to use 2 times this 1.01 because it's H2. So we're going to go 2 grams of hydrogen for 1 mole. Then we're going to multiply the tops. 3 times 2 is 6, times 2 is 12, and divide by the bottoms, which is 32 times 1 times 1, which is 32. And 12 divided by 32, I believe, is 0.375 grams of hydrogen. So look at the difference here. When we did moles, we had 6 moles of hydrogen. And when we did grams, we actually, starting with the same number as 3 grams of oxygen versus 3 moles. So we got two very different answers. And you also can see it took a lot more work when we had to deal with grams and a lot less work when we just had to deal with moles. And that boils down to the fact that, right, both of these are using the balanced equation. In fact, everything we're going to do should use the balanced equation. But we also had to use the periodic table here and the periodic table here. Whereas when we were just doing moles, then all we needed was something from the balanced equation. We did not need to get into the periodic table for that. We did need to get into the periodic table for for grams. All right. So in summary, a mole to mole relationship comes from the balanced equation. If you need to change from one color to another, use the balanced equation for that. And if you need a gram to mole relationship, you're going to need the periodic table. All right, so now a whole different situation here. We have aluminum oxide, and we have oxygen still, and we also have hydrogen, or aluminum rather. We have aluminum. So this thing is starting us off with 9 moles of oxygen. So that's our given. The number in the question, that's all by itself, 9 moles of oxygen. And we need, where are we going? What's the how many? The how many is moles of aluminum, right? So how many moles of aluminum? So we need moles of aluminum. So as you could probably tell, on this situation, we're starting with moles of oxygen and we're going to moles of aluminum. This is going to be a one-step process where we just need the balanced equation. If we had grams involved, we would need the periodic table, and it would be more than one step. But since it's moles, we only need one step. So we're going to start with our given, which is the 9 moles of oxygen. And we need to cancel out moles of oxygen and go to moles of aluminum. And those numbers come from, because it's a mole to mole relationship, the balanced equation. So for every 4 moles of aluminum, we will use 3 moles of oxygen. So oxygen cancels and we have moles of aluminum. That's what we needed. So 9 times 4 is 36, and 36 divided by 3 is 12. So the answer here is 12 moles of aluminum. So these mole to mole situations are really easy to do because they don't need the periodic table. You don't need grams, so you don't need the periodic table for these mole to mole situations. When you need grams, then you do need that. So here's basically the same question, although instead of moles now, we have grams of oxygen. Our given is 9 grams of oxygen. And we need to go, instead of just moles to aluminum, we got to go all the way to grams of aluminum. All right, so we're going to start with the 9 grams of oxygen. All right, and we need to get out of grams. So getting out of grams of oxygen, using the periodic table, we can get to moles of oxygen. Again, on the periodic table, oxygen on the bottom will have basically 15.998 something or other. So we'll just go 16.0 grams in 1 mole. Oops, that should be 32. My bad. Let's erase that. All right, so that should have been that should have been 32 grams because each one's 16. It's O2. So we need 2. Now, that gets rid of grams of oxygen. We're in moles. From moles, we can get out of moles of oxygen. Oops. Out of moles of oxygen and into moles of aluminum. Even though we need grams at the end of the day, moles of aluminum will take us close. And that relationship is right here. There's 4 moles of aluminum for every 3 moles of oxygen. That gets rid of moles of oxygen. Now we're in aluminum, so we need to go back to our periodic table. And if you look at aluminum on the periodic table, it's number 13. It weighs 27, basically 26 point something. So that's grams, and we want grams, so we want grams on top. So the 27 goes on the top, and then 1 mole, because we're dealing with the periodic table, is on the bottom. Now notice we didn't have to double this or anything because aluminum is just the one element. It's not multiple atoms as it would be there or there. So moles of aluminum are gone. We have grams of aluminum. So 9 times 4 times 27 is 4 times 27 is 972. And then 32 times 3 is 96. And when you divide those, you get 972 divided by 96 should give you 10.1 grams of aluminum. All right, so again, look at how much work we do with moles to moles. We just need one balanced equation equivalent. And when we do grams to grams, we need that balanced equation plus 2 periodic table. Periodic table there and a periodic table here. All right, so basically this is sort of like the highway. If you're starting at moles, it's just one step, moles to moles. You're going to use the balanced equation, and you're going to come back out with moles of a different substance. If, however, you need grams, you're going to go to the periodic table, convert grams to moles. Then you're going to use the balanced equation to go moles to moles. And then if you need to keep going to grams, you're going to use the periodic table again and convert grams from moles. All right. So here is another thing. So we still got our aluminum here and our oxygen and our aluminum oxide. But notice here, this time, we're starting with the aluminum oxide. So our given is 5 moles of aluminum oxide. Oops. Al2O3. And we need moles of aluminum. So we're needing moles of aluminum. So this is going to be one of the simpler situations because we're just doing moles to moles. We just need the balanced equation. We don't need the periodic table. So starting with our given, and our given is the 5 moles of Al2O3, we need to get out of moles of Al2O3 and into moles of aluminum. And that relationship comes from mole to mole balanced equation. So we got 4 with that one, and we got 2 with that one. That cancels out moles of aluminum oxide. We have moles of aluminum, which is what we needed. So we're just going to do this math real quick. 5 times 4 is 20. 20 divided by 2 is 10. So that takes 10 moles of aluminum to react to make 5 moles of aluminum oxide. All right, so these mole to mole things you can almost do in your head, right? Because you're seeing here that if I have 5 of these, how many of those did I need? And it's a 2-to-1 relationship. So you would need twice as much aluminum. Perhaps you see that. All right, but now we again turn to grams. Moles turns to grams. So this is going to be a little bit harder. So we need grams of aluminum. That's where we're headed. And we're going to start with, use that other green. We're going to start with grams of aluminum oxide. All right, so we start with our 5 grams of aluminum oxide. We got to consult the periodic table. If you think about this, right? We started with grams of aluminum oxide this time. So we got to go to the periodic table, figure out what that weighs, get that to moles. And then from those moles, we can go to the moles of aluminum and then again go to grams using the periodic table. So aluminum on the periodic table weighs 27. In aluminum oxide, there's 2 aluminums. It's Al2O3. So that is a total of 54 grams. And then the oxygen is 16. There are 3 oxygens in this Al2O3. So 3 times 16 is 48. And then we're going to add those up. And we're going to get, 102 grams. So we want that in the bottom, the 102 grams in the bottom. And that's how many grams there are in 1 mole of Al2O3. Because we use the periodic table, that's how many grams there are in 1 mole of Al2O3. Now, what we're going to do is use this balanced equation, and this balanced equation is going to get us out of that green and into the black that we need, the aluminum. So we need to go from moles of aluminum oxide, and that is a 2 from the balanced equation, and we're going to go to moles of aluminum, and that's a 4 from the balanced equation. So grams of aluminum oxide are gone, moles of aluminum oxide are gone. The only thing standing right now is moles of aluminum, but we need grams of aluminum. This came from the balanced equation. So we're going to need to go one more step, and that next step is going to use the periodic table for aluminum, and 1 mole of aluminum on the periodic table is just the 27 grams. 27 grams. All right, so some fancy math here. 5 times 4 is 20, and 20 times 27 is 540 as our numerator. That's multiplying the tops, 27, 4, and 5. And then 102 times 2 is in the denominator, so that's 204. When we divide 540 by 204, we get the answer of 2.64 grams. So that's how much aluminum we need if we want to get 5 grams of aluminum oxide. So if someone asked us for 5 grams of aluminum oxide and we had to figure out how much aluminum we needed in the back room, we would need 2.64 grams of aluminum. All right, so here's another one using propane now. So let's keep some colors consistent here. We're going to keep oxygen red. So there's oxygen, and propane. Let's make that blue. And in this case, we have 6.70 moles of propane. All right. And we have excess oxygen, and we're looking for water vapor. So water vapor, I should have done blue for that, but we'll just make it purple. So we're going to water vapor, right? Moles of water vapor. So we need moles of water vapor, and we're starting with moles of propane. It says excess oxygen, which is basically just making a point that you're not going to run out of oxygen before you run out of propane. And we'll talk about that in a little more detail here in a bit. So we have moles of propane to start. We need moles of water. Mole to mole, this will be a quick one. So this will just be the one-step problem. So we start with moles of propane. And we need to get out of moles of propane, and we got to get into moles of water. And we're going to use the balanced equation to do that. So we know there's 4 moles of water for every 1 understood. There's no number there, so it's understood to be a 1 mole of propane. And we're going to do that math. And 6.7 times 4 divided by 1. So that's going to be 26.8 is how many moles of water we would get. All right, so there's that. Now we change from moles to grams. So do you expect this will be more difficult or less difficult? I am assuming that you're good with, oops, I meant to change that to grams. Let me do that right now. So let's go grams of water. And there we go. All right, so we're looking for grams of water. We're starting with grams of propane, so that's this one. And we're going to grams of water, which is right here. All right, so we need grams of water, and we're starting with 6.70 grams of propane. 6.70 grams of propane. So we're going to need the periodic table this time because we got grams to grams. We're going to start with what's given, the number from propane. Now notice you can go from anywhere to anything. So we could have gone from propane to oxygen, could have gone propane to carbon dioxide, could have gone water to carbon dioxide. It doesn't always have to be something from the start to something from the finish, right? You can go from any of these compounds to any other compound. So we need to cancel out grams of C3H8. So if you go to the periodic table, carbon weighs 12, and in this case, there's 3 of them, so that's 36. And then H weighs 1, and in this case, there's 8 of them, so that's 8. And then when you add up 36 plus 8, you get 44 grams. So that's going to go on the bottom. And the 1 mole goes on the top. So now we got to go out of moles of C3H8. And we got to get into where we're headed. And in this case, we're headed to water. So we need moles of water. And while this came from the periodic table, this is going to come from the balanced equation. So 4 moles of water for every 1 mole of propane, right? Because it's understood 1. So moles of propane are gone, grams of propane are gone. We now need to get to grams of water. So we're again going to consult our periodic table for this last step. We want grams of water. Everything on the periodic table is good for 1 mole of water. And if you go there, hydrogen weighs 1, and there's 2 hydrogens in water. So that's 2. Oxygen weighs 16, and there's 1 oxygen. That's 16, so it's a total of 18 grams. That's 18 grams of water in 1 mole. So we do this math. 6.7 times 4 times 18 is 6.7 times 4 times 18 is 482.4. And then 44 times 1 times 1 is 44. So we're going to divide 42.4 divided by 44. And that gives us 10.9. So the answer is, if we start with 6.7 grams of propane, we should end up with 10.9 or 11.0 grams of water, depending how you want to round that. All right. I hope that's helpful to you. That is stoichiometry in a nutshell.